Sorry, getting situated. Okay, so screencast on fuel cells and rechargeable batteries. This is part A. The objectives: describe how a hydrogen-oxygen fuel cell works, describe the workings of rechargeable batteries, including the relevant half reactions, if you remember back to redox, and then to discuss the similarities and the differences between fuel cells and rechargeable batteries. Okay, so both fuel cells and batteries, they both use oxidation reduction reactions to generate electrical energy. Electrochemical reactions are potentially a cleaner source of energy than fossil fuels, potentially. Fuel cells convert the chemical energy of a fuel directly into electrical energy. The fuel has to be oxidized or reduced, it's stored outside of the cell, and it has to flow continuously through the cell. Okay? Sometimes it's referred to as a flow battery. So let's take a closer look at the hydrogen fuel cell. The overall reaction is hydrogen reacting with oxygen to produce water. Okay, with a change in enthalpy, negative 286 kilojoules per mole, the negative telling us that it is exothermic. Okay. The benefits to this fuel cell are that it is a non-pollutant. There are no additional environmental pollutants from the operation of the fuel cell. That's contrasted with fossil fuels that increase the carbon dioxide and greenhouse gases, as well as some acid rain with the sulfur dioxide that can be introduced into the environment. The challenge is to develop this as a large-scale economical fuel source. And there you go, you have an example of what they're trying to do with a car. So the hydrogen fuel cell, there's two types, basic electrolyte, and there's an acidic electrolyte. Other things to note about this fuel cell, fuel cells, is that they, they require constant replenishing. Okay, so we have to have the flow of hydrogen and oxygen continually flowing. I don't know why it's doing that, dear me. Okay, so it requires constant reflowing, and the only, well, I shouldn't say the only, but one environmental impact is that, I see. Sorry, I had a cable where it shouldn't have been. The only environmental impact is the source of hydrogen is from cracking ethane. So there is some of that fossil fuel processing that goes on. Okay, so let's look at a basic electrolytic fuel cell. See, we have hydrogen coming in, oxygen coming in, and these have to, again, be continually flowing. You've got an electrolyte membrane, okay, and this electrolyte membrane here is typically a porous, I'll spell porous right, porous matrix that is saturated with the electrolyte. Okay, so that's a porous matrix saturated with the electrolyte that allows the hydroxide that is generated to flow through to the anode. Okay, so much like a Voltaic cell, oxygen coming in, hydrogen coming in, water being continually exited, as well as heat, because it is an exothermic reaction. At the cathode, we're reducing oxygen, okay, to the hydroxide. At the anode, we've got the hydrogen with those hydroxide ions producing water, overall making a voltage that can then be used for electricity. The electrodes are graphite coated with a metal. How about an acidic electrolyte cell? What changes? Well, here I've got fuel in and air in. Okay, so oxygen, hydrogen, being oxidized to the hydronium ion and electrons. This oxygen then is reacting with those hydrogens that are produced at the anode with the electrons to make water. So water and heat comes out the top. So it's kind of a different flow pattern going on. The electrodes in this case are particles of platinum. Well, they're coated with particles of platinum. Okay. So, moving on to batteries. Definition of a battery: a series of one or more portable voltaic cells that use an electrochemical reaction to generate electricity. There are two types. Primary can't be recharged. Secondary can be recharged. Okay, and the idea here is that I don't have that continual flow of hydrogen, oxygen, or air like I did in the fuel cell. Batteries, it comes kind of already charged. So voltaic cell review. Hasn't been that long since we did electrochem, so this should all make sense. If it doesn't, you need to either come see me or look back over redox notes. So let's talk about secondary batteries. These are the type that can be recharged. The design of the battery needs to allow for the reactions that occur during the discharge to be reversed during the charging. There are three examples of secondary batteries: a lead-acid battery, nickel-cadmium battery, and lithium-ion battery, and you are going to need to know specifics about each of these batteries. Looking specifically at the lead-acid battery first, at the anode, I have a lead electrode that's solid. The cathode is made up of lead-4 oxide, PbO2, which is also a solid. The electrolyte is 6 molar sulfuric acid. Another way to describe this would be concentrated sulfuric acid. So, at the negative electrode, this is the anode, oxidation will occur. I'm going to have that lead reacting with the sulfate ion from the acid to form my lead 2 sulfate and electrons, with the voltage being generated. At the cathode, reduction will occur with that lead 4 oxide reacting with the hydronium ion and sulfate ion with the 2 electrons to form that lead 2 sulfate. Notice that the same solid is produced in both the anode and the cathode. So the overall reaction of the discharge of the cell, adding these up, I get the lead plus the sulfuric acid plus lead 4 oxide being made into lead 2 sulfate and water with an overall plus voltage. So why does that allow for recharging? When I am charging the lead battery, I start with that lead sulfate, and then I make at the cathode that solid lead and the sulfate ion. At the anode, I'm also starting with the lead 2 sulfate with water, forming the lead 4 oxide as the solid. Okay, so I'm kind of building up that anode again. releasing hydronium ions, sulfate, and the 2 electrons. So the overall equation for the charging of the battery is the lead-2 sulfate. This isn't exactly balanced. There should be a 2 here. And I believe that makes it balanced. So that lead-2 sulfate forming that lead solid and that sulfuric acid, and then also the lead-4 oxide. Flipping back here, so it really regenerates the cathode and the anode during the recharging. Benefits of the lead-acid battery: it's good for heavy power applications such as a car battery. It's relatively cheap. Drawbacks: it's kind of heavy. Okay, lead is a heavier, more dense metal, and it does contain toxic and corrosive materials. Toxic being the lead, and the corrosive materials being the sulfuric acid. Moving on to the nickel-cadmium batteries. The anode in this battery is made of the cadmium metal. The cathode is a nickel-3 oxide hydroxide, okay, as a solid. And then the electrolyte is the hydronium ion, and that's in aqueous form, okay, because the electrolyte better be able to move, and that's made of potassium hydroxide. What goes on at the anode? Well, we have this oxidation reaction, cadmium, reacting with the hydroxide ion to form the cadmium hydroxide. The nickel 3 oxide hydroxide, nickel 3 oxide hydroxide, reacting with water to make the nickel 2 hydroxide solid and ending up with a hydroxide ion. Overall, here's my equation. I gotta know these. Gotta know this equation, gotta know this equation. Just have to. Okay? So, moving on to the lithium-ion battery. Lithium is very reactive, i.e. very positive reduction potential, so batteries containing lithium have the potential to generate very high voltages. However, the reactivity of lithium needs to be considered in the design of the battery. Can't have water, because that would react with the potassium. So this has to use an organic polymer electrolyte. Okay, so this is important to know. Uses an organic polymer electrolyte. Can't have any oxygen in the system because, again, lithium being reactive would make lithium oxide, so the batteries are sealed. Okay, there can be no pure metal lithium at the anode. It's combined with graphite. So, at the anode, lithium metal is mixed with graphite to make Li6. And the reaction that you can see could be written LiX C6, reacting to form X lithium ions plus 6 carbons plus X electrons. Okay. At the cathode, we get the lithium ion. By the way, this is mixed in polymer. You know how usually we see AQ? This means that the solvent is polymer. Could write it up here if I wanted to. Okay, plus the MnO2, the solid, goes to LiMnO2 solid. And this has to have an electron on this side. That would do it. Okay. So the electrolyte is a polymer electrolyte, meaning there is no water. So these two overall equation will be Li XC6 plus NNO2 goes to 6 carbons and LiMNO2 solid. So, lithium metal is oxidized to the lithium ion at the anode. Lithium ions migrate through that polymer electrolyte from the anode to the cathode. And at the cathode, manganese 4 oxide is reduced, forming LiMNO2. And this is what your battery would look like. You've got your negative graphite matrix with lithium dispersed throughout it, polymer electrolyte allowing the movement of your lithium ions, and then your positive electrode with electrons obviously traveling from the anode to the cathode. So let's look at the differences between these. In a fuel cell, external fuel source is needed. Products need to be removed. Okay, this is continual feeds of the fuel, continual removal of the product. This is better for continuous power needs. Rechargeable batteries, both the fuel and the products are contained in the battery. This is better for short-term power needs. Let's look at, we're going to add the similarities. Okay, both generate electrical power from chemical. Okay, so both utilize redox equations. Okay. Both, I don't know why I didn't E there, require anode, a cathode, and an electrolyte. So they both have to form really electrolytic, Voltaic cells, electrolyte. And both generate current. Okay. And both are based on the separation of redox reactions. Okay. With the flow of electrons through an external circuit. Okay, so advantages for fuel cells: more efficient than combustion, there's no pollution, lower density. Disadvantages: hydrogen is an explosive gas, hydrogen is transported and stored in heavy containers, and there's technical issues for fuel cells: catalyst failures, leaks, corrosion, and they are usually more expensive. Let's summarize rechargeable batteries. Battery type lead. Advantages: it can deliver large amounts of energies over short periods of time. Disadvantages: heavy mass, and lead and acid are environmentally hazardous. Then we have the nickel-cadmium. Has a longer life than a lead-acid battery, but it's expensive. Cadmium is toxic, and there's a relatively low voltage that's delivered. For your lithium-ion battery, the advantage is its low density, it's high voltage, and there's no toxic metals. But it is expensive, and there is a limited lifespan. And that ends our screencast on batteries and fuel cells.